Recording. Recording. Okay, guys, not too many questions today, but if you've got questions, you know your little flip notebook, write it down and ask me later. Okay, are we good? Okay, what's the difference between equivalence point and endpoint? Matt, that's
endpoint will indicate changes at equivalence point when they change.
Yeah, what's the relationship between them?
You want your endpoint to your equivalent point to be in your endpoint.
Yep, we want the endpoint to overlap the equivalence point. Now we're going to be learning about this thing called a titration curve. First, you have to understand sharp endpoint. Has anyone read ahead and seen the word sharp endpoint?
Slightly, yes.
What is it?
I have not read the definition.
Okay, when you've done a titration, let's say we're using phenolphthalein, okay, and we get a pink colour change. Yes? Because we're going, let's say we're titrating in the burette, we've got a base. Remember it's pink when it's gone too basic? How easy is it to overshoot?
Very, yeah.
Plus or minus 1 drop. Yes? If you add half a drop, you might be in the clear, but if you add a full drop, you've overshot it, it's dark pink. This is the term sharp endpoint. It means, guys, and quickly if you're taking notes, where the addition of a very small amount of volume of acid or base produces a large change in pH. This only happens when we have a strong acid or base. Why do you think it wouldn't happen when we have a weak acid or base? It doesn't change the pH as much, it's a very gradual change in pH. Okay, how can we determine when the equivalence point is? We said through an indicator. Okay, I'm going to briefly explain how indicators work for a diagram. Let's say that in our conical flask we have HCl. Yep. Is that a strong or a weak acid? Why is it a strong acid? Okay, that's actually why, but what defines it as a strong acid? It readily donates its proton in water. We won't forget that. Okay, now, what does it actually exist as, HCl? Okay, now an indicator, does anyone, oh we didn't talk about this in year 11, but indicators are a substance whose colour depends on the concentration of H+. Does that make sense? They're going to change colour depending on the pH. At the back? Does it make sense? Now, you don't have to write all of this down. You're actually probably wasting time by writing it down because you're not listening and these notes are on Edmodo. Now, indicators are weak acids. I'm going to show you how an indicator works. So, we have a weak acid. Can I just do it like this? Guys, I just want you to look. Don't write notes, please. You've got notes. They're already up. Indicators are weak acids. Does that represent a weak acid? We have WA, but we have a H. So that's showing that it's H is attached. Now, if I had a solution of indicator, because it's a weak acid, what would it exist as mostly? Alex? What would it exist as mostly if I had a solution of weak indicator?
Water? What do you mean?
Okay, mostly water, but I mean out of this, what are the two forms that it can exist as if it's an acid? Jake?
Aqueous?
Okay, if it's a weak acid, if it's an acid, what will it do in water? What will the arrows look like?
Half.
Okay. And what will be the conjugate base of this weak acid? Wa minus. And? Excellent. What will be the most, the majority in that solution besides water will be this or this? Gemma, why will it be mostly this? Someone help her out.
Because it's a weak acid, it isn't as ready to donate as hydrogen as a strong acid would be.
Excellent. So in solution, it's mostly this, a little bit of this. So mostly where? Mostly where? All right. So we put a couple of drops. Where and where? All right. But it's mostly HCl. Now, we are titrating with NaOH, strong base. NaOH in the burette will look like what? Will it look like NaOH, Eleanor? Connected. Will it look like NaOH? No. What will it look like? Yes, into? What will be the two ions? Guys, help her out.
Na and OH.
Excellent. Okay, that's what it'll exist as. Why will it exist like that? It's in aqueous, it's completely soluble, no precipitate. Okay, so as we're pouring this down, let's graph this out. This is what's meant by a titration curve. We might have, let's say that it is 0.1 N NaOH, and we'll say 20 mils of 0.1 N HCl. Now, let's say that we had something that detected pH, a pH meter, and then we were graphing pH versus volume of NaOH added. At first, Tim, what would the pH be inside the conical flask? It would be low. What would it be exactly? We can work it out. Jake, you're working it out. Who said 1?
Me.
Excellent. Why is it 1?
Because it's 0.1.
HCl is monochromatic. We learnt this last time. Girls, you following? Okay, so we start off with a pH of 1. Then, as we're adding more NaOH, what's happening to the pH? Why is it increasing? Besides the fact that it's basic, what determines pH?
It's being less constant. The HCl is becoming less constant.
The H2O plus is becoming less concentrated. Why?
Because there's more solid.
No, not because there's more hydroxide, but because some of the H plus, if you do the ionic equation, is reacting with the OH to produce water. This is what's meant by the neutralization reaction. Okay? The neutralization reaction is the process. Why can't I spell neutral? Why can't I spell it? Neutralization reaction, we get neutral products. Is salt neutral?
Yep.
H2O. So, when we add it, we're removing this. Is that right? So over time, you get less of these. And then eventually, when all of these are gone, when all of the H plus is gone, what's that point called, Sandy? When all of the H pluses have gone. When there's only neutral products that neutralise each other, it's the point that we want to help her out. Equivalence point. Okay, so at the equivalence point, we're only... Shh, guys, please listen at the back. I know you are because you got that right. But the equivalence point is when we only have these in our conical flask. Is that right?
Yes.
Okay, so we should have a pH of what?
7.
Excellent. And how many mils of NaOH am I going to have to add to make it pH of 7? Have a look at how many mils of HCl I have.
20.
Who agrees with 20? Pop your hand up.
Oh yeah, it's 20.
20 mils to reach equivalence? Amy, why 20? Excellent. So the moles, it's a 1-to-1 mole ratio, right? So the moles of NaOH is the same as the moles of HCl. Are we happy with that? Okay, now, so once we've added 20, we have reached equivalence point. At this point, guys, we have removed all of the H plus from HCl. Are there any H pluses left?
Yeah, but there's one H. OH.
Oh, but what else? What else do we have in there?
OH.
The indicator. Guys, we have the indicator, which is a weak acid. So at this point, what's the OH, incoming OH, going to do? It takes these away. Remember, they don't have a choice. Because they're only weak acids, because they don't really dissociate in water. Are we happy with that? Then, as we added, guys, there's not much indicator. How much indicator do you add? 2 drops. So as we add 1 drop of OH, all of these OH simultaneously takes all of these off, changing all of these to what? To Wa without the H, which is a different colour. So, they're weak acids, their acid form is one colour, and their base form is another. Okay, that's why we get the end point. Do we have questions about that? What's the end point again, guys? Very simply. Indicator changes colour. Has to overlap the equivalence point. It changes colour over a range because at the first drop you might add, it might not get rid of all of it. Then you add another drop and it gradually changes colour. But really, it should be a very small range. Like phenolphthalein, you add a drop and it literally just turns pink. But this is sharp endpoint. This is very good for a titration. We can be quite sure of the equivalence point because even if we add only a drop over, we've overshot it, but the effect is only a small number of moles excess. If it was a gradual change, we might overshoot by adding a lot of moles in excess. Do you get what I'm saying, Alex?
So if you've seen that your solution just changes, like because of the indicator in it, if it just changes colour, if it has just changed colour, it's not that much of a big deal.
Exactly.
Yeah.
Exactly. Because we have, it changes pH very rapidly with a small number of drops because of the way indicators work. Okay, now we've got these ranges of indicators, okay? But I'm going to go through this 2011 question. Oh, and I'm going to show you this. So, guys, in your data book, Matt, are you listening?
Yes, miss.
In your data book, you have the name of the indicator along with the colours. So, when this indicator, thymol blue, is in an acid, when we add HCl to it, when it's in the acid range, it looks red. Yeah? When it's in a basic range, it looks yellow. That's the way your chart works. So, phenolphthalein, guys, if I'm adding NaOH to phenolphthalein, so we have phenolphthalein, it's with HCl at the moment, I'm adding NaOH, what's the colour change that I want? From what colour to what colour? Colourless to, not yellow, red, phenolphthalein. No, guys, you've got to just use the colours from Vika. So we want to see colourless to red. Okay, how about something that looks, Eleanor, stop it. If I have as unknown solution and I add it to bromothymol blue and it looks yellow, is it an acid or is it a base? If I add it to bromothymol blue, unknown solution, is it an acid or is it a base? Acid. That's the way it works. Because it looks yellow. And in its acid version, i.e. everything below this value, it'll look yellow. Does that make sense? So, with that in mind, give yourselves a minute to try and answer this question. This was a VCAR question. Exactly. So, guys, how are we going? In thymol blue, it looks yellow. What does that tell us? So, its pH has to be higher than what? Then, it looks yellow in methyl red. So, what does that tell us? So, it's even higher than 6.3. Then, phenolphthalein, it's colourless. 8.3 is the highest, 6.3 is the lowest, therefore what's the option? C. Excellent. So that's the way you answer that type of question. Oh, I think excellent. Okay, titration curves. Now guys, I just have a quick activity to hand out for titration curves. Now, I want you to just focus carefully. What I've done is I've cut up the titration curve, i.e. that thing, and I've put different reactions with the curves. Okay? What you have to do is match the reaction with the curve and then state what indicator would be best, i.e. what indicator has an endpoint around the equivalence point. If it's pH of 7, if we want to look at a pH of 7 at the equivalence point, which indicator would we use? Bromothymol blue. Would we use phenolphthalein? No, because that tells us a higher pH. Okay, let's head this out.
In between the pH range, like what happens?
As soon as you get it started, yep.
What does it mean if it's in between the pH range? What would it be then?
Oh. If you just say in between colourless, no, you don't say that, you just say in between colourless and blue. So,
Would it give an indicator that's in between them, or?
yes, you need to have it overlapping your equivalent. Yeah. So have a look. Yep. Yep.
So what question? Stairs and you just like. What are you gonna pour it down? Drinking my soul.